as opposed to these kind of visible, observable regimes, there are also hidden regimes that are even more subtle. For example, people say that there are a lot of these retail traders, Robinhood traders, that are buying call options on these small, stocks such as GameStop, for example, such as AMC. Is that a regime? Does that cause a market regime change that affect many strategy? Apparently it did, but it's hard to put your finger in it. What does a regime call Robinhood traders buying call options? What's the name for that regime? Or a large family office articles liquidate and causing a contagion among many prime brokers, all liquidating together. Is that a regime? Does that cause fundamental market structure change, at least for that period? And more generally, some of these hidden regimes are specific to affecting only some strategy. Why is it that my profitable strategy that had worked for several years suddenly stopped working in the last few months? Is that because of regime change? So these regimes, these hidden regimes, are not easy to identify. They are not observable. They may only affect certain strategies. They may benefit some strategies and negatively affect other strategies, but they may have no impact on yet other strategies. These hidden regimes, therefore, are hard to identify, but actually they could be easier to predict, using a large number of factors. So our job as machine learning, as the financial machine learners, is to predict these hidden regimes. And why is it that it's easier to predict hidden regimes than these observable regimes? And one of the reasons is because not everybody are trading the same strategies. And as George Soros say, reflexivity is what kills a lot of predictions, right? If you can predict a regime, typically the regime might go away. Let's say everybody is predicting a bullish regime and they buy up the stock ahead of time. Well, there's no marginal buyer left, and that might cause a bearish regime to come about sooner than expected. So the fact that if you can predict an observable regime is like able to predict the market direction. The fact that you can predict it means that the market direction will change, and it also means that the observable regime will change. Whereas if you are talking about predicting hidden regimes that may only affect your strategy and other similar strategies, not everybody are trading those strategies, not everybody is making the same predictions, and so those predictions might still endure and stand, and it will not be arbitraged away. So now, everybody wants to predict regimes, whether they're observable or not. The traditional, and there are many methods that have been proposed traditionally to make this kind of regime predictions. One of the more popular method is state space models. A particular type of state space model is hidden Markov model, for example. But these models have been very weak. They are not very predictive because the only input so far are prices, right? The traditional hidden Markov model try to use prices to identify hidden regimes. But because prices are very just one dimension, these models are very weak. Now there are further improvement to that, and actually applying more features to hidden Markov model, and that is the paper that I identify here at the bottom, called Feature Selection in Jump Models. That's a paper that one of the co-authors of this paper sent it to me after we published our work on conditional parameter optimization. Professor Pettercombe sent his paper to me, and it's very interesting because it, in parallel with our work, they also incorporate many features in the format of a hidden Markov model in predicting regimes, but specific to jump models. So you might want to check out these kind of parallel methods. For us, our objective is actually very direct and very simple. How do we identify regimes implicitly? in order to adapt our trading models parameters. We are not so much interested in identifying the regime per se, because as I said, these regimes are hidden, they are very subtle. Just because you identify them doesn't really lead to any actionable item. So the actionable item that we actually want to engage, want to deploy is parameters. What parameters should be changed for our strategy if we can identify this regime? Now, going back to why traditional hidden Markov model or other in general state space models are not so predictive, and how we can improve on it, and why machine learning can improve on it. Well, one reason, as I already mentioned, that machine learning model can make a stronger prediction than traditional models, state-space model, is because it can incorporate a much larger set of predictors or features, as we call it in machine learning. And the other one, and the other reason is that very often machine learning model can handle nonlinear interactions. Of course, we are not thinking about logistic or linear regression, which can still be considered machine learning. We are talking about more complicated machine learning models such as random forest or even deep learning networks, all of which can handle nonlinear interactions between among predictors. These nonlinear interactions are important to capture because a lot of times the predictors have a conditional dependence. And a simple example would be, let's say you want to predict whether tomorrow is going to be a volatile or not volatile regime. Well, it might be that if today's fixed level is under 20, a set of features would be useful for predicting tomorrow's fixed level. However, if fixed is above 20, a different set of features might be important. So there are these conditional dependence, which are difficult to tease out manually and difficult for a traditional state-based model to model, but they are ideal for a machine learning algorithm such as random forest to take care of. So these two factors, these two reasons, the ability to incorporate much larger pool of predictors without overfitting because of advanced feature selection algorithms that I talked about in my earlier webinars, and also the fact that you can take into account nonlinear interactions as well as conditional codependence of predictors are what led us to using machine learning for regime identification and parameter optimization, which is the work that I'm going to talk about today.